Watch me calculate 11 derivatives, where each one gets more difficult than the previous one. Let me know in the comments how far you could make it through this video, and which ones you found challenging. Derivative number 1. Let's start off with just a simple polynomial function. I know I can differentiate all three of these terms independently. When I differentiate the first term, 3x squared, I'll use the power rule, which tells me I can take the exponent, multiply it by the coefficient, and then reduce the exponent by 1. So the derivative of 3x squared becomes 6x to the power of 1. Minus, when I differentiate 4x, the derivative of 4x is 4, and the derivative of any constant is 0. So my derivative is 6x minus 4. Derivative number 2. Before I find the derivative of this expression, let me just rewrite those terms in a way that'll make using the power rule easier. X to the 6 over 2, I could rewrite that as a half being multiplied by x to the 6. 5 over x cubed, let me just take this power of x, bring it to the numerator, and that'll make the exponent become negative. And the square root of x, I can write that with a rational exponent as just being x to the power of a half. Now I can differentiate all three terms independently of each other, and when I use the power rule, the derivative of a half x to the 6, 6 times a half is 3, so I get 3x to the power of, reduce the exponent by 1, it becomes 5. The derivative of my second term, negative 3 times negative 5 is 15. Keep the base of the power as x, but subtract 1 from the exponent becomes negative 4. And my last term, x to the half, the coefficient becomes a half, base of the power is still x, minus 1 from the exponent, it becomes negative a half. And then I'll just rewrite this so it doesn't have any negative exponents. So it becomes 3x to the power of 5 plus 15 divided by x to the 4 plus 1 over 2 root x. We could get a common denominator, but I'll leave it with the three terms separately. Derivative number 3. This time we have two functions of x being multiplied together. So when I calculate the derivative of that product, I'll use the product rule of differentiation. I've highlighted the first function in blue and the second function in red, and now I'll do my derivative. The product rule says do the derivative of the first function, which would be 6x minus 4. That needs to be multiplied by the second function, plus the derivative of the second function, which is 2, and that needs to be multiplied by the first function. And I'll just expand this into standard form and collect. So let me find these four products. And that would give me 12x squared plus 30x minus 8x minus 20. And now let me find these three products, which is 6x squared minus 8x plus 2. Now I'll just find like terms. I've got a 12x squared and a 6x squared that I can collect together. That's 18x squared. I have a 30x minus 8x minus another 8x. That's 14x. And then negative 20 plus 2 is negative 18. Derivative number 4. This time I have a quotient of two functions of x, so I'll need quotient rule. And this is also the first time that we see some trig functions. Let me highlight the top function in red and the bottom function in blue. Quotient rule says do the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. So let me follow that format. The derivative of the top function, sine x, is cos x. That has to be multiplied by the bottom function. Minus, I do the derivative of the bottom function. The derivative of 1 plus cos x would be negative sine x. That needs to be multiplied by the top function, which is sine x. And that all gets divided by the bottom function squared. Now I'll simplify the numerator by expanding and collecting my like terms. Cos x times 1 is cos x. Cos x times cos x is cos squared x. And then this all simplifies to plus sine squared x. And then hopefully you notice right here that I'm highlighting in yellow, that's the Pythagorean identity. Sine squared x plus cos squared x is 1. So I could rewrite this as cos x plus 1 over 1 plus cos x all squared. And now you should notice the factor in the numerator is just like the factor in the denominator. 1 plus cos x can cancel out with one of the factors of 1 plus cos x in the denominator. Something divided by itself is 1, so in the numerator I still have 1, and in the denominator I have 1 plus cos x. Derivative number 5. Once again, I have two functions of x being multiplied together, so I'll need to use the product rule of differentiation. Let me just highlight those two functions of x in different colors. Product rule tells me I have to do the derivative of the first function, and this is the first time when the base of our power is a function of x itself. So we have a composite function here, so we'll need chain rule. When I find the derivative of 3x minus 2 cubed, that would be equal to, bring the exponent down, 3, keep the base of the power exactly the same, minus 1 from the exponent, but then I have to multiply by the derivative of the base of the power. The derivative of 3x minus 2 is 3. That's the derivative of the first function. That has to be multiplied by the second function. Plus, now I have to do the derivative of the second function. Bring the exponent down, keep the base. The exponent minus 1, 2 minus 1 is 1, times the derivative of the base of the power. The derivative of x plus 4 is just 1, so I don't have to write a factor of 1. But then that has to be multiplied by the first function. Now, instead of trying to expand and collect this into standard form, which would be a lot of multiplication, it'll be easier if we put this into factored form. This plus sign is separating my two terms. I've got a term here and a term here. Notice they both have factors of 3x minus 2, and they both have a factor of x plus 4. So I will start by common factoring out a 3x minus 2 squared and an x plus 4 from both terms. Let me divide this first term by my common factor. When I do that, I get 9 times x plus 4. When I divide this second term by my common factor, I get 2 times 3x minus 2. Now I'll just simplify what I have inside the square brackets. I get 15x plus 32. Derivative number 6. This time I have a power of a function where the base is a quotient of two functions of x. So I'll need to be using chain rule, and within the chain rule, I'll be using quotient rule. The chain rule tells me when I differentiate this, I would bring the exponent down, I would keep the base of the power exactly the same, reduce the exponent by 1, but then I have to multiply this by the derivative of the base of the power, which is x minus 3 over 2x plus 1. So now let's focus on finding that derivative, and I'll need quotient rule for that. I'll rewrite this first part of my derivative, and now when I find the derivative of this quotient, if I follow quotient rule, it says to do the derivative of the top, which is 1, multiply that by the bottom, minus the derivative of the bottom, which is 2, multiply that by the top function, and that's all over the bottom function squared. And now I just have to simplify. I'll expand and collect this numerator. If I do that, I would get 2x plus 1 minus 2x plus 6. I could collect that together, and that would simplify to just 7. And that's all over 2x plus 1 squared. Now let me multiply these fractions. When I multiply these numerators, I just get 28x minus 3 cubed. And when I multiply the denominators, I get 2x plus 1 to the power of 5. Derivative number 7. They're starting to look more difficult. I have 3 terms that I need to differentiate, but I can do those all independently. The derivative of the first term, it might help if I actually rewrite sine cubed x. What that means is we have 3 factors of sine x, so I could write it as a sine x being cubed. And now it'll be obvious when I differentiate this, I just follow the chain rule, which tells me to bring down the exponent, leave the base of sine x, but change the exponent to 2, right? Reduce the exponent by 1. And then multiply by the derivative of the base of the power. The derivative of sine x is cos x. Plus, now I have to do the derivative of my second term. This one's different. Sine of x cubed is different than sine cubed of x. Right? This time it's the argument of sine that's being cubed, not the whole sine ratio. So when I differentiate this, I'll do the derivative of the outer function. The derivative of sine is cos. I'll leave the inside function exactly as it is, leave it as x cubed. But then I have to multiply that by the derivative of the inside function, which is 3x squared. Minus, I had a constant factor of 4, so I put that in front of the derivative. And I need to multiply that by the derivative of sine of cos of 2 to the power of x. Start with the outermost function. sine. The derivative of sine is cosine, so I can change it to cosine of, keep the argument the same, cos of 2 to the power of x, but then multiply by the derivative of the argument. Let me actually make this smaller to give myself some more room. The derivative of cosine of 2 to the power of x. The derivative of cosine is negative sine. Leave the argument, but then multiply by the derivative of the innermost function, 2 to the power of x, which is 2 to the power of x times the natural logarithm of 2. There's the derivative. Let me simplify it. Nothing to do with the first term. The second term, I'll move the 3x squared to the front. In the third term, I have 2 negative factors. That'll make a positive. And this 4 is a 2 squared, which I can combine with that power of 2 by adding their exponents. Derivative number 8. Before I differentiate, let me start by rewriting those terms. The square root of e to the power of x, I could rewrite that as e to the power of x to the power of a half, plus 4 multiplied by e to the power of x to the half. So this first term, I can use the exponent rule that tells me I could just multiply those exponents together. Now I'll differentiate both of the terms. To differentiate both of those terms, let me remind you of a couple things. The derivative of e to the x is e to the x ln e, but ln e is 1, so the derivative of e to the x is itself e to the x. If we're differentiating e to the power of some function of x, that would be equal to e to the power of that function of x multiplied by the derivative of that function of x that is in the exponent. So the derivative of my first term is e to the half x times the derivative of a half x is a half, plus 4 times e to the power of x to the half, and then multiply that by the derivative of x to the half, which is a half x to the negative a half. And then let me simplify this a bit. I could rewrite this term back to where it came from, which was the square root of e to the x. That's being multiplied by a half, so I'll divide it by 2. Then when I simplify this term, 4 times a half is 2. I'll take this power of x to the denominator, and this will leave me with 2 e to the root x divided by root x. Derivative number 9. I have 2 terms that I have to differentiate. Let's start by focusing on the derivative of the first term, which we'll need product rule for because it's a function of x times a function of x. I need to do the derivative of a half secant x, which is a half derivative of secant x is actually secant x tan x. That needs to be multiplied by the second function, so multiplied by tan x, plus the derivative of the second function, so derivative of tan x is secant squared of x. And that gets multiplied by the first function, which is a half secant x. Before I even think about this second term, let's just simplify what we have here. I've got 2 terms where I could common factor out a half secant x from both of those terms. When I divide the first term by a half secant x, I get tan squared x. When I divide the second term by a half secant x, I just get secant squared x. And the Pythagorean identity tells me that tan squared is equal to secant squared minus 1. These 2 secant squared x's could be combined together to be 2 secant squared x. And now if I expand my first product, a half secant x times 2 secant squared x would just be secant cubed x. And my next product will be minus a half secant x. All right, so all of that is just the derivative of this first term. Now we have to find the derivative of this second term. Now before I do this, I may want to make some room. So this constant factor of 4, when I'm doing the derivative, the constant factor can stay out front, and we'll multiply that by the derivative of this function of x, the natural logarithm function. Remember, the derivative of ln x is 1 over x, so the derivative of this function would be 1 over the argument times the derivative of the argument. So it would be 4 multiplied by 1 over secant x plus tan x, multiplied by the derivative of secant x plus tan x. The derivative of secant x is secant x tan x, plus the derivative of tan x is secant squared x. Now if I look at that factor, notice both terms have a secant x, so I could common factor out a secant x. So I'll get plus 4 secant x, and when I divide both of those terms by secant x, I get tan x plus secant x. And don't forget, that's all being divided by secant x plus tan x. So that factor of tan x plus secant x can cancel with that factor in the denominator. So I'm left with just plus 4 secant x. And that 4 secant x can be collected with that negative a half secant x to give me 3.5 secant x. So I'll write that as plus 7 over 2 secant x. And there we have it. There is that whole derivative. Derivative number 10. This is the first time that y is not explicitly defined in terms of x. So if I want to differentiate with respect to x, I'll have to use implicit differentiation. Let me actually start by rewriting that natural logarithm. Since the argument of that logarithm is a quotient, I can separate that using the quotient rule of logarithms to write that as ln of x minus ln of y. And now I'll start differentiating all of the terms with respect to x. The derivative of ln x is just 1 over x, minus the derivative of ln y with respect to y would be 1 over y. But I want to differentiate it with respect to x, so I have to multiply this by dy over dx. And that's equal to the derivative of a power of e. I keep that power of e, and then multiply by the derivative of the exponent, which I'll need product rule for. The derivative of x is 1. That needs to be multiplied by y cubed. Plus the derivative of y cubed is 3y squared dy over dx times x. On the right side, let me distribute this power of e to both terms. And I'll get a common denominator on the left, so I can write that as a single fraction. So I'll multiply this term top and bottom by y, this term top and bottom by x. So that gives me y minus x times dy over dx over that common denominator of xy. And that's equal to, when I distribute to both of these terms, e to the xy cubed y cubed plus e to the xy cubed 3y squared x dy over dx. Let me multiply both sides by xy. Let me multiply this term by xy. I get xy to the 4 plus, I also need to multiply this term by xy. I'm going to have an x squared and a y cubed. Now I need these terms that have a dy dx on the same side of the equation and the terms that don't on the other side. And notice I took the liberty of common factoring out that dy over dx at the same time. Let me make some room to do the final line. All I have to do is divide both sides by that factor, and then dy over dx is isolated. And there you have it, there's the derivative. Derivative number 11. Alright, you've made it to the most difficult derivative. This derivative is complicated because we have an inverse tan function, and I also have an inverse hyperbolic sine function. Another layer of complexity is that we have an x to the power of x. Let's actually start by looking at that x to the power of x. If I'm going to need the derivative of that at some point, so let's find the derivative of x to the power of x right now. Now, that's not a power function, it's not an exponential function, so how do we work with it? I'm actually going to rewrite this as an exponential function by changing the base of this power from x. I'm going to rewrite it as a power of e. I can change that x. X is the same as e to the ln x, right? That's equal to x. And don't forget that that's being raised to the power of x. And then based on my exponent rules, I know that I can multiply those exponents together. So that's equal to e to the x ln x. And now I could find the derivative of that. The derivative of that, I would keep the power of e and multiply by the derivative of the exponent, which I would need product rule for. The derivative of x is 1. That would get multiplied by ln x, plus the derivative of ln x is 1 over x, and that would get multiplied by x. Now these x's would cancel, and this e to the power of x ln x, I can rewrite that back as just x to the power of x. So the derivative equals x to the power of x times ln x plus 1. Let me move this off to the side, because we will need that at some point. Other rules I'm going to need for this, I'll need to know what the derivative of arctan of x is. The derivative of arctan of x is equal to 1 over 1 plus x squared. And lastly, the last derivative rule we'll need is the derivative of the inverse hyperbolic sine function. That's equal to 1 over the square root of x squared plus 1. So with those three rules, we should be able to find this derivative. Let's start with the first term. It's a logarithmic function. The derivative of a logarithmic function I know is going to be equal to 1 over the argument of the log, which is arctan of x to the power of x, multiplied by ln of the base of the log, which is ln 5. And that needs to be multiplied by the derivative of the argument of the logarithm. So I have to multiply by the derivative of arctan of x to the power of x. Well, the derivative of arctan, we wrote over here, is 1 over 1 plus x squared, but it won't be x squared this time. It'll be x to the x squared. So it'll be 1 over 1 plus x to the x squared. I could just rewrite that as x to the power of 2x. And then, of course, based on chain rule, when I was differentiating that trig function, I differentiated the outside function with respect to the inside function, but now I have to multiply that by the derivative of the inside function based on chain rule. So that has to be multiplied by the derivative of x to the x, which we figured out is x to the x times ln x plus 1. So this is the derivative of my first term. Let me maybe write that as a single fraction, and then I'll make some more room to work with my second term. And now let's focus on the second function. The inverse hyperbolic sine function, I know its derivative is 1 over the square root of x squared plus 1. But in this case, x is tan x. So when I differentiate this, it's going to be 1 over the square root of tan squared plus 1. But because the argument wasn't just an x, it was a tan x, I have to use chain rule, which then says multiply this by the derivative of tan x, which is secant squared x. And now I actually see a nice identity we can use here. Tan squared x plus 1, based on the Pythagorean identity, is equal to secant squared x. So I can rewrite this as secant squared x over the square root of secant squared x. Now we have to be really careful here. The square root of secant squared x is always going to be a positive value. But if we were to cancel out that square root with the squared, then it's not going to guarantee that that's always a positive value, so it wouldn't be equivalent. So I can replace this, not with just secant x, but with the absolute value of secant x. And let me zoom out, and there we have it. There is the complete final derivative. Let me know in the comments how far you made it, which one of these you found the most difficult, and what series you want to see me do next. Jensen Math!